So let's see how much of this you remember from last week. How do we find the mean? We add them all up, and we divide by, remember the term? Divide by n. N in this case equals what? 5, because there's 5 items in the list. So 12 plus 16 plus 19 plus 23 plus 30 is 100, I believe. Divided by 5 is 20. So our mean is 20. How about the median? Well, here's one, you could just cross off the ends and work our way into the middle. We can actually look at it and see that the middle is what? 19. Because I already put them in order, it was really easy to find the middle. Remember, if I hadn't done that, the first step would be to put in order. The second step is to find the location. And the location is found by doing 0.5 or 1/2 times n. So in this case, that would be 0.5 times 5 is 2.5. If you recall, there's two possibilities here. This one, it's a decimal, which means we are going to round up. So it'd be the third number in the list. 19 is the third number in the list. If that was not a decimal, if that was a whole number, what would we do? It'd be between that location and the next location, if you recall. So let's write down 19 is our median. Mode. There is not one. You are correct. There is none. Range. Largest minus the smallest. 30 minus 12 is 18. A range of 18. And finally, the fun one, standard deviation. Standard deviation was a 6-step process. Anybody remember what step 1 is? Find the mean. You've already found that. It is 20. What's that? Mean? No, it was 20. Okay, sorry. You had me panicked for a second there. What's step 2? Subtract the mean from each. So we have what? 12, 16, 19, 23, 30. And we will subtract 20 from each of those. -12 minus 20? -8. 16 minus 20? -4. 19 minus 20? 1. 23 minus 20? It's 3. And 30 minus 20? It's 10. Now, this isn't part of the calculation, but if we wanted to double check here, what would we do? If we add those up, that should add to 0. What's step 3? Square them. Very good. -8 squared is 64. -4 squared. 16. -1 squared. 1. 3 squared. 9. What's that? 3 squared is 9. And 10 squared is 100. Step 4. Find the sum or add them up. Find the total, right? If we add those all up, we get 190, correct? Now, the step that confused a lot of people is step 5. What is step 5? Divide by n minus 1. N in this case equals 5, so we're going to divide by 4, which is going to give us 47.5. That actually had a name. That value right there is called what? It's called the variance. To find the standard deviation, though, we have to do step 6. Square root it. Square root of 47.5 is 6.9, approximately 6.8 something. .89. Remember, our rule of thumb for standard deviation is you go 2 digits past, 2 decimal places past the data. So this data was all whole numbers. So our standard deviation, we would go to the nearest hundredth. The mean, we would go to the nearest tenth if it didn't come out to be a whole number. Usually my math lab, they'll tell you what to round off to anyway on each problem, so you don't have to worry about that. So we found the mean, median, and mode were measures of center. And remember, we're talking about this bell curve and where the middle of it is. Remember, below the bell curve, there's this number line of values of the data. The height of the curve is how many items in our set take on each of those values. The mean, median, and mode, if this curve is symmetrical, should be in the center, describing where on the number line the center of that curve is. The range and the standard deviation are descriptions of spread or dispersion or width. They're telling us how wide that curve is. So we're going to combine that basic idea of center and that idea of spread and see how does that really break down this curve. How does that apply to stuff? There's something called the empirical rule. And it's based off of probabilities that are more complex than what we're going to get into in our couple of weeks of statistics in this course. But the empirical rule allows us to take the center and the spread of this curve and actually come up with some very useful information from it. Now, there's something called the approximate empirical rule, which is what I use in pretty much every other course I teach. For this textbook and this course, they use something called the precise empirical rule, or the exact detailed empirical rule. So they're going to use some numbers a little bit more difficult to remember, but they're pretty much the same. So we're looking at our bell curve. And the center of our bell curve is that mean, and we're going to use the mean as the center. And what we're going to do is we're going to go out away from the mean in each direction in steps that are equal to 1 standard deviation. So what I've done here, this is 1 standard deviation below the mean. So I'm going to put -1 standard deviation. I subtracted 1 standard deviation from the mean. I go out another step. I've subtracted 2 standard deviations. I was going to go SD for standard deviation. One more step is 3 standard deviations below. Now we do the same above. I'm going to go a standard deviation above. I'm going to add the standard deviation. So +1 standard deviation. And +2 standard deviations. And +3 standard deviations. What does this mean? Well, first of all, let's identify those values down there. Each data set will have a mean and a standard deviation. So let's say that the data set we're looking at, let's look at test scores. Test scores on our next test. And let's say that that next test, historically, over the last, 15 years or so that I've taught this course, has a mean score of 78, with a standard deviation of 8. So what that means, the center of this curve is going to be 78. That's the mean. The standard deviation is 8. So if I go down a step, I'm subtracting a standard deviation. So I'm taking my mean, which is 78 for this case, subtracting my standard deviation, which is 8, which is going to give me 70. If I go down another step, that'll be another standard deviation. Subtracting 8 again would be 62. Going down another step, subtracting one more standard deviation, subtracting another 8, this would be 54. Going the other direction, I'm adding a standard deviation. So starting at the mean of 78, if I go up a standard deviation, I'm adding 8, which would be 86. Adding another 8 would be 94, not 96. And adding another 8 would be 102. So those benchmarks, again, they're determined by the mean and the standard deviation. Those will be different for every set of data we look at, depending on what the mean and standard deviation of that data are. So these numbers are determined by the data. By the set that we're looking at. The next piece we're going to put in here is always the same. This part is constant. The percent of the data that's going to be between the mean and one standard deviation below is always going to be 34.13% of the data. That's if the data is normally distributed. So if it fits in this bell curve. Since it's symmetrical, it's 34.13% between the mean and one standard deviation above. Going below from one standard deviation to two standard deviations, there's always going to be 13.59% of the data in that range. And of course, the same above, 13.59%. Between 2 and 3 standard deviations away from the mean, it's always going to be 2.15% on either side. And finally, more than 3 standard deviations away from the mean. So out here, this is going to be 0.13% on both ends. So what does that mean? Well, that means that for this test, with a mean of 78 and a standard deviation of 8, I'm going to expect 34.13% of my students to score between 78 and 86. I'm going to expect another 13.59% to score between 86 and 94 on average. Now, one class may be slightly different than others, but over the years, I would expect that percentage to fall into each group. Now, there's something when we deal with probability and statistics, something called the law of large numbers. You hear me use the term on average a lot. And what I mean by that is if we do this enough, those proportions, those percents will even out. Now, right now, there's one person in each of the 3 locations over the network, and there are 7 people in the room with me, so 10 people total. Now, with only 10 people taking the test, I don't expect that exactly 3.4 of you are going to end up between 78 and 86. That's not reasonable. You might all do very well. I mean, with a small group, there's a chance you might all do very well or very poorly or scattered all over the place. But if I gave this test to 1,000 students, I would expect that out of 1,000 students, about 34.13% are going to score between 78 and 86. Does that make sense? Okay, so now let's take a peek at another application of this. Let's say that you get out of school and you want to go get a job. And you are offered a job in a different area. So you're not really sure, how pay is in that area. So you want to look at starting wages in that area. This is actually going to go with the empirical rule, which the law of large numbers kind of overlays everything. So we're looking at starting wages in that area. You have been offered $13.40 per hour. You're not sure whether that is a good offer or not. So let's say that we look at the mean and the standard deviation. We look at other starting wages in the area and we find the mean and standard deviation. We find that the mean is $12.20 and the standard deviation of all those wages is $1.20. So what does this mean? That means if we draw out our bell curve, the center of that curve is going to be what number? $12.20. If I go one step this way, that's going to be what? I'm going to subtract $1.20. I'm going to subtract my standard deviation. This will be $11. If I go another step, it's going to be $9.80. And one more step will be, each step I'm subtracting my standard deviation, so this will be $8.60. Okay? If I go this way, a step, I'm adding the standard deviation, so the first step will be $13.40. The next step, $14.60. And the next step, $15.80. Good. Remember, we said these are the numbers that are determined by the data set, the mean and the standard deviation of that data set. The percents that go in here are always the same. So 34.13, 13.59, 2.15, and 0.13. What is this telling us about our offer? Well, $13.40 falls where? That's right here. Right there. Well, what information does that give us? Well, if I look at that, that's telling us if I add up all of these percents that are on the lower end, these are the numbers that are smaller than 1340. If I add all those up, that is 84.13%. That's saying that salary, $13.40, is bigger than or equal to 84.13% of all the starting salaries in that area. So in other words, 84.13% start at a lower or smaller wage. Would you be happy with that? You're better than 85% basically of people in that area? Sure. What if you talk to somebody and they say they're making $9.80 an hour? What's that tell you about them? Well, that tells you, if we look at this here, 1.13 plus 2.15, that's only 2.28. That means that only 2.28% of people in that area are making less than them. So they probably could do better. If you talk to somebody who's making $15.80, that's telling you that only 0.13% of the people in that area are making more than them. Or I could subtract it the other way. If I add all these percents up, that would be 99.87% of people in that area are making less than them. Does that all make sense? The 84.13. This is where we're at right here. So we're adding up all the percents that are smaller than it. The percents, yeah, just the percents. So, and the way I did it so quickly is, since this is symmetrical, this is the middle. I know these have to add up to 50%. That's half. So I just did 50 plus the 34.13 to make it quicker. Same with this 99.87%. I didn't actually add up all of these percents. I just know that the whole thing's 100, so I took 100 minus 0.13. So let's say you want to buy a house. You do your research, and you're looking for a 3-bedroom, 2-bathroom house. You do your research and you find that in the area that you're looking, the mean price for a 3-bedroom, 2-bath is $124,000. You find that the standard deviation is $19,000. You find a house that you absolutely love, but it is priced at $162,000. The realtor tells you that you better put in an offer on it right now or it's going to be gone. Using what we just looked at, I'm going to give you a couple minutes. Do the probabilities, do the curves or whatever. What is your argument against what the realtor is telling you here? So first of all, the percents in here are not going to change. They're all the same as what we've seen before. What numbers are going to go across the bottom here? What goes in the middle? 124,000. I'm just going to put 124 to abbreviate. What's going to go here? Minus 19,000, so 105. Here, 86, and here, 67. How about going this way? 143, and here, 162, and here, 181. So what was your argument to your realtor? Well, 162 is the price of the house. Where does that fall? Right there. It's on the higher end, definitely. Can you give me more specifics? It's not necessarily that it's 97.72% higher, but it is higher than 97.72% of all other houses. In other words, 97.72% of other 3-bedroom, 2-bathroom houses in that area will be cheaper than that. So chances are you're going to find one that's cheaper that you like. So this mechanism can be used to compare numbers, to find percents. You could even convert them into probabilities if we wanted to go that far. So you can see how this compares to other items in that same population in that same group. You can't compare starting salary in another area to starting wage here, because different cost of living, different sets, different labor pool and different demands and stuff like that. Same with houses. You can't compare the cost of a house here to a cost of a house other places. I'm going to give you an example. I was offered a job about a year and a half ago in Washington. Very impressive starting salary, but the average cost of a 3-bedroom, 2-bathroom house in this area is about $124,000. I looked into it. That's why I know. Out there, it was, depending on what region, within 10 miles of the place that I was given the job offer, it was in the $400,000 range. So the cost of owning a home was tremendous. You could get 20 miles away, which was about a 35 or 40-minute drive away. It's now in the $300,000 range. So, you can look at, you can't compare the cost of a home here to there because it's just different circumstances. You couldn't compare the salary here to there because the living expenses were very different. So those are things you have to consider. You have to compare it to within what is there already. Another mechanism that does that is something called Z-scores. Like we said, you can't compare two things that are from different populations or that occur under different sets of conditions or rules. We have to compare things that are within their own population, their own circumstances. And a Z-score is another very quick mechanism that not only does that, but allows us to compare numbers to each other as well. And it's very similar to what we were doing up here. In fact, the house that we were looking at there, it's Z-score. The Z-score of an object is equal to, it's the number minus the mean of the population it's coming from, divided by the standard deviation of the population it's coming from. So if I wanted to look up here for this example, the house was $162,000. Subtract from that, what was the mean? $124,000. Divide that difference by the standard deviation, which was $19,000. We subtract 162 minus 124 is $38,000. Divided by a standard deviation of 19,000, which gives us 2. It's a 2 or a positive 2. What is that telling us? That is telling us that this house this house's price is 2 standard deviations above the mean for that area. It's a positive 2, so it's 2 standard deviations above the mean or greater than the mean. Well, how does that help it? That means it's expensive. In this case, it's not a good thing. It's a bad thing. In some cases, it's a good thing. It depends on what you're looking at. If you want it to be cheap, well then, yeah, it would be a very bad thing. If you're selling, it's probably a good thing if you get a price that's above the mean. Let's say that you're looking to buy a house again, and you're going to compare 2 houses, but they're in different areas. So you've got one house that's, let's say you're getting a job in an area, you've got one house that's east of town, and one house that's west of town. You've looked at the drive time and all that, and it's all pretty much comparable. Driving to work will be about the same time. It's just the different neighborhood and the cost of real estate in each of those neighborhoods is different. The one on the east side of town is priced at $108,000. The one on the west side of town is priced at $140,000. Well, the one on the east side looks like it's cheaper. But let's say that the mean for houses east of town, the mean of houses in that area that are that size, is $120,000. And the standard deviation is $12,000. Let's look at west of town. Let's say the mean of houses west of town is $150,000 with a standard deviation of $8,000. We can't really compare the 108,000 to the 140,000 because they're in different neighborhoods. The east side of town, obviously a cheaper neighborhood to live in. Who knows why? Whether higher crime rate, worse schools, bad roads, who knows? The west side of town looks like it's more expensive. And again, possibly the same type of reasons. So comparing this to within houses in each of their area, the one on the east side of town, we take its price, the 108,000, minus its mean of 120,000, and divide by its standard deviation of 12,000. Well, 108 minus 120 is a negative 12,000. Divided by the standard deviation of 12,000 will give us negative 1. The negative means we're below the mean. Negative 1 means 1 standard deviation below the mean. On the other side over here, we have the $140,000 as our price, minus that mean of 150,000, for a standard deviation of 8,000. We subtract 140 minus 150 is negative 10,000 over 8,000. We divide negative 10,000 divided by 8,000 is negative 1.2. That house is one, the negative still means below. That's 1.2 standard deviations below the mean. So what that's saying is that compared to the houses in that area, this one is more unusual. It's further below the expected value, even though it's only 10,000 below, and this one is 12,000 below, because there's less variance, less deviation in those prices. That doesn't necessarily mean it's a better deal. I mean, maybe you don't have kids, so you don't care how good the schools are, or whatever. You know, maybe you don't go out and don't go to the local parks. You don't care if there's parks in the area or whatever. Doesn't mean it's a better deal. It just means that this one is more unusual compared to the other houses in that area. Does that make sense?
Todd, you lost me on the 1.2.
Okay. So I did the 140,000 minus 150,000 is negative 10,000.
Yep.
Then I divided by that standard deviation of 8. That should be 1.25, shouldn't it? Is that where I lost you? In fact, my math was off?
Yeah.
Negative 10,000 divided by 8 is negative 1.25. Thank you. So that's 1.25 standard deviations below the mean. The little hamster is pretty much dead by this point in the night, so the wheel's barely turning. Okay, so let's look at another example. Let's say you're a manager of a department store, and you've been to Walmart or Shopko, anything like that, Target. You need to get rid of one of your salespeople. You've decided, you've got it narrowed down to 2 people. We'll call them person A and person B for confidentiality. And you decide that whoever does the worst job, I'm a math teacher, means I'm not supposed to have much of a sense of humor. Whoever does the worst job next week is out the door. Person A works in toys and sells $2,400 worth of merchandise. Person B works in electronics, and that week sells $4,200 in merchandise. So it looks like person A is out the door, right? No. We need to compare them to the other people in that department, in that group. So let's say you look store-wide, and you find that for salespeople in toys, the mean sales is $3,200, and there's a standard deviation of $300. For people in electronics, there's a mean sales of $5,500 and a standard deviation of $500. So now we're going to take a look at how each of them compares to their own population. We can't compare toy sales to electronic sales because electronics are generally in higher demand, usually higher priced. I mean, I'd much rather buy a toy truck for my kid than buy a new television set. Depending on the time of year, I mean, you don't know what the sales are. Christmas time, of course, toys might be higher sales than electronics in some cases, but who knows? So we want to compare them to the other members of their own population. So we're comparing the person who's selling toys to other people selling toys, and the person selling electronics to other people selling electronics. So we're looking at this, finding the Z-score for each. So for the person in toys, it's 2,400. That's their value minus the mean of 3,200 divided by a standard deviation of 300. 2,400 minus 3,200 is -800. Divided by the 300 standard deviation gives me -2.67. I'll round to 2 decimal places. I want you guys in your notes right now to calculate the Z-score for salesperson B in electronics. So for person B here, 4,200 minus what? 5,500 over 500. We subtract, what's the difference? -1,300, okay. Over 500, we divide, we get -2.6 exactly. So the person in toys is still worse. They are 2.67 standard deviations below the mean of their peers. The person in electronics is 2.6 standard deviations below the mean of their peers. Not much worse, but salesperson A is definitely worse. So they're out the door. I'd probably find any way to get rid of this person soon anyway. But now, the thing is, when you do it this way, there is always going to be somebody on the lower end. You know, you're never going to have a whole sales staff that's all above the mean because the mean is calculated from within them. And by definition, about half will be above and half will be below the mean. So you have to keep that in understanding as well, that there are going to be people with negative Z-scores. Everybody that has a negative Z-score, if you fire them every week, you're going to lose half your staff every week. Let's take a peek. Let's have you guys do one here. You're going to take let's look at your college entrance test. And let's say you take a math test and an English test. And on your math test, let's say you score a 24. And on the English test, you score a 32. Now you might look at that and say, hey, I scored way better on English. But you don't know the level of difficulty. The English test might have been an easier test. So they want to compare you want to compare yourself to everybody who took both tests. So we're looking at all the people who took both of those tests. The mean score on the math test is an 18 with a standard deviation of 3. The mean score on the English test is 25 with a standard deviation of 4. So in your notes, figure out for me which one is a more impressive score. And actually, we're at that point where it's time to take our break. So let's go ahead and take our break. We'll come back at 6:30, and when we come back, you can go ahead and calculate this. I'll give you a few minutes when we come back to figure out which one of those is more impressive. So let's go take our break. We'll come back about 6:30.